Hello, Chemical Engineering 176. This is Professor Kusung Yang in the Department of Nanoengineering at UC San Diego. Today I'm going to show you how to model the low-pressure chemical vapor deposition using COMSOL software. Before we begin with LPCVD simulation, first we need to have a brief introduction to the COMSOL software, so you will know how it works. So our first step is to start the COMSOL. So if you use UCSD lab computers, you click the Start menu and you should be able to find the COMSOL multi-physics. You click it, open it, and the first interface you will have is this new model interface. So here we have the two options, model wizard and the black model. The model wizard is very useful because it will give us the step-by-step instruction to build a new model. So we will use the model wizard here. So let's click the model wizard. The next step is to select space dimension. In COMSOL, we have several types of space dimensions, like the 3D, 2D axisymmetric, 2D, 1D axisymmetric, 1D, and 0D. For example, in the LPCVD simulation, we need to use a 2D axisymmetric. After doing this, and the next step is to select physics. For example, here we could choose the transport of diluted species to model the mass transfer. And then we click the study. We have the option for the study. The first one is the stationary, which means it's not time dependent. The other one is time dependent. Suppose we choose the first one, stationary, and then we click the done. Then we finish the whole model wizard process. So after building your new model, we come to the main interface of the COMSOL software. The top shows the file menu and some shortcut. The most left is the model build window, which is the most important window of the COMSOL because we will mainly work on the model build window. And here we have several options which will be talked about next part. And the middle is the setting window. Here we will set the parameters for each option in the model builder. The right part is called graphics. Here we will show the geometry or the results. For example, in the COMSOL, you can produce very nice figure which will be showing here. And the bottom, the right of the bottom part is the message, progress, and log. So which basically shows the information of your simulation task. So up to now, we finished the first part, the start your COMSOL and to know the COMSOL. In this part, we will learn the model builder and its operations. In the model builder, we have four options, including the global definition, component, study, and results. In my perspective, these four operations correspond to the four steps in any kinds of computer simulations. That is the first step to set your parameters. The second step to build your model. The step is to do your calculation, which is study in the COMSOL. The last step is to analyze your results. In the global definitions option, if you do a right click on it, you can choose options to set the definitions like parameters, variables, and functions. Of course, as the name implies, all these operations are global, which means that they will be applied on the all the geometrical models and the physics you have selected. We take parameters as an example to show how to set definitions. So if you double click this parameter button, then you will have this setting windows. So here you can input parameters manually, or if you click this button to load parameters from a text file. For example, you can load all these parameters from the boot reactor parameters. The second option of the model builder is the component. The component also contains several options, including the definitions, but remember here, the definition in the component is local. And you can think about what's the difference between the local definition and the global definitions. The concept is very similar to the case in your programming language. You have the local variable and you also have the global variables. And besides the definitions, we also have the geometry, material, physics interface, and the mesh. In the geometry, we will build our own geometrical model here. And if you want to add the new physics model, for example, in addition to the mass transfer, I also want to add the heat transfer model, then I can do this by right-click on the component. To add variables in the definition of component, you need to expand the definition by clicking this triangle. For example, in the LPCVD simulation, we need to add the variable delta silicon, which is the silicon deposition rate. By the way, so it is always a good habit to add some descriptions for your variables. Here we go through the geometry option. To build a geometry, you can always right-click on the geometry to select the geometry operation unit, like the rectangle, square, line, or even dot. But remember, the geometry is based on the space dimension you have selected in your model wizard process. For example, in the LPCVD, we use the 2D axis symmetric. These two figures come from the LPCVD simulation. The left is the 2D model for a boat reactor. The right is the 3D model. To better understand the geometrical models, you need to recall the coordinate system from your mathematics course. For example, in the LPCVD, we use the cylindrical coordinates. In the 2D axis symmetric geometry, the R label represents the radial coordinate, and the Z label represents the height coordinate. In the LPCVD simulation, the 2D geometrical model can be built by following the step-by-step instruction from this document, Boat Reactor LPCVD, which can be found in the course 176 website. Here we go through the physics in the model builder. In the component, we can add multiple physics. For example, in the LPCVD, we will use the heat transfer, mass transfer, and laminar flow physics. To add a new physics, you can always do this by right-click on the component. And for each physics, you can double-click it to set the parameters or to choose the domain. Here is the last part of the model builder, study and results. The study in the COMSOL means the compute. In the study option, if we double-click the step 1 stationary, then we should have this window. In this setting window, we can set the parameters here. For example, in the LPCVD simulation, we can change the temperature, reactor temperature TR as 800, 850, and 900 K, which means we will do the calculations at these 3 different temperatures. Then from the analysis, we will be able to analyze how the temperature will change the results, like the silicon deposition rate. Now we move to the results. Here we introduce 2 widely used options, dataset and export. The dataset can help us select the target data that we want to analyze. And the export will export the data into the text file for the further processing. For example, in the LPCVD simulation, if we want to analyze the data into the wafer area that is called domain 2, highlighted in green here, then we can do the right-click on the dataset and choose the solution and do the selection to choose the domain 2. And if we want to analyze the results in a nice 2D figure, then we need to do the right-click on the results and choose the 2D plot group. In this setting window, choose the data from the domain 2, that is wafer area. The parameters here will be automatically selected from your setting in the study. So here the V0 equal to, which means I have done a calculation at V0 equal to. And if you choose the reactor temperature in the study, then here will show the temperature. Okay, next is to right-click on the 2D plot group that you just created and choose the surface. In the expression window, choose the object that you want to analyze. For example, if I want to analyze how does the silicon deposition rate will change, then I will choose the dirt silicon here. By the way, you can click this triangle here and search for the expression, which will save your time. And after doing that, you click the plot, then the COMSOL will show this nice figure in the graphics window. So it will show at V0 equal to, with this figure shows the silicon deposition rate. The unit is meter per second. So now let's see how to export data from the COMSOL. To export data, we need to do a right click on the export option and then choose the data. So then in the setting window, we will choose which data we want to export. For example, in this LPCVD simulation, I have done calculations at the inlet flow velocity V0 equals 1, 1.5, and 2. And I would like to study how the parameters will influence the dirt silicon, that is the silicon deposition rate. So to do this, we need to choose the dirt silicon in the expression and also select the parameters V0. So if you want to get all the data at these three parameters, then you select all of them. And if you only want to get the silicon deposition rate at one value, then you only select the one parameters, like the 1 or 1.5. After this setting, then we need to choose the path in which we can save the data, and also particularly pay attention to the data format. And to use our MATLAB code to read this data, we need to choose the grid and spreadsheet data format. And you need also set the range for the R and for the Z, so that our MATLAB can read this data correctly. The MATLAB code can be downloaded from the Chemical Engineering 176 course website. So now we finished the basic introduction for the COMSOL. In our next part, we will operate the COMSOL software and do 2 more practical examples to give you a better understanding how we will run the COMSOL simulations. So in this part, I will show you how to solve the pre-lab question using COMSOL. Essentially, we will use COMSOL to solve the Laplace equations. And the pre-lab question can be downloaded from the course website, and click here and download the PDF file. Open the Pre-Lab PDF file and read it carefully. When we do this COMSOL simulation, you are supposed to finish the pre-lab questions and submit your answer to the Dr. Zhu and in this PDF file. So if you read it again now, you probably will find several familiar words. The first one is called the steady state, which means this is the stationary. So probably you will recall that we have met this word in setting the COMSOL wizard, so which is the one option in the study. The second one is called the Laplace equation, which is a mathematical tool to do the calculations. As we talk about it in the COMSOL, the mathematical tools belong to the physics. So now we have some ideas to set the COMSOL wizard, and we will use the Laplace equation in the physics and use the stationary option in the study. So next we analyze what kind of geometrical model we need to set. In the question 2, you will immediately find that this is a 2D square model. So in the space dimension, we will choose the 2D model. And to solve the Laplace equation, it's very necessary to set the boundary conditions. So here we notice that in this square model, the left and bottom boundary condition is 100 Celsius degree, and the top and right boundary conditions are 50 Celsius degree. So up to now, we already know which space dimension we need to set, which physics we need to choose, and which study option we need to use. So we will be able to solve the temperature distribution in this square model. Okay, so now I will show you how to operate the COMSOL softwares. And I open the COMSOL. The first interface is the new model option. So here we will choose the model wizard. And to solve the pre-lab question, we already know that we need to select the 2D model. And the physics, we are going to choose the Laplace equation, which should belong to the mathematics. And if you cannot find it, just let's do the search. Okay, so I put the Laplace and click the search. See, I found this classical Laplace equation. Okay, I click them. And here, since we are going to study the temperature distribution, so I will choose this source term, the dependent variable quantity. I will choose the temperature. So I select the temperature as T. So T temperature here. And the unit, of course, should be the key Kelvin, the absolute the temperature unit. And the source term quantity is none. And click the study, and we will choose the stationary, and click down. So we finish the model wizard process. Okay, so now we come to the interface of the COMSOL. In this pre-lab question, we do not need to set the global definition because it's a very simple task. And then we come to the component. In the component, we need to build a 2D square model. And to do this, we on the geometry, we do the right click and select the square. In the square, I input the side length as 3 meter. 3 meter, which means we could have the 3 unit lengths. 3 unit lengths, which means we will have the 4 points on each side. And this will make us have a direct comparison between our COMSOL model with the pre-lab model. So I click build selected, then I finish this geometrical model building. And our next step is to set the boundary condition in the Laplace equation. So in the Laplace equation, and there's no boundary condition here, then we can do the right click and choose the boundary condition here. Say we set the boundary condition 1, and here selection we choose all boundaries. So now we have the 1, 2, 3, 4 size, and one size is showing in this green, and which is should be the 100 K, right? 100 Celsius degree. And here in the COMSOL is Kelvin, but here we can still use the 100 K because it's much easier for us to compare the data. But we need to know that, okay, in the COMSOL, the unit of the temperature is absolute temperature is Kelvin. Okay, for the 2, it is also 100 K, and then for 3 should be the 50. But here I should not set the 50 here, because if you set 50, then the boundary 1, 2 will also be changed as a 50. So here I delete the 3 and 4. And I do the similar right click the boundary condition. So now we build the boundary condition 2, all boundaries. This time I will remove the 1 and 2. And for the 3, I put the 50 here. And for the 4, it's also 50. So now we finish this boundary conditions. And the next step is to do the study, which is calculation. Okay, after building the model, after setting the boundary condition, next we come to the study. In the study, it's a stationary. I only need to click here. So the compute. So we are compute. And here to show the message part, show the progress. Oh, wow, nice. So here is the results produced from this results. It shows the temperature distribution in this square. And this color bar shows that the below is the low temperature and red is the high temperature. So you can compare this COMSOL figure with your pre-lab question figure. and you produced from the MATLAB code. So you compare them and see whether the COMSOL give you the right results or whether you did it correctly. Alright, then we finished this pre-lab questions, and next we will do the LPCVD simulation. Alright, so now we come to the part 4, LPCVD tutorial. In this part, I will show you a tutorial simulation of the LPCVD using COMSOL. The tutorial model can be downloaded from the course website, in which all the parameters and geometrical model are already built. So your job is not to build the model again, but to learn how to do the calculation and how to analyze the results to better understand the COMSOL simulation process. Now I'll show you how to run the LPCVD tutorial simulation. First, you need to download the tutorial model from the course website and then open it. We click the file, open, and choose the one you download from the course website and click open it. Okay, so it might take a while, depends on how fast is your computer. Initialize the graphic user interface. Okay, so now we open the this model, and here the global definition, the parameters it's already set, and you can take a look at all these parameters and have a better understanding what does this mean. And in the component, we already built this 2D geometry model, and so no need to build them again. And then in this tutorial model, our job is to do the calculation. So we click the study 1, step 1 stationary, and here we will input the parameters here. So here the input the parameter is V0, which means inlet axial flow velocity. So here you can put the number 1, 1.5, 2, or 2.5, any number you want, but you had better do a literature review and see what is the best velocity range. And beside this inlet velocity, you can also change other parameters like the react temperature or the concentration or the wafer spacing. So suppose now I change the V0. Okay, I input here 1, 1.5, and 2. And next I click the compute. Yes, we click the compute, and here you will see the message progress log, and the table here it shows some the information about this simulation task. And this simulation might take you from the 20 to 30 seconds, depends on how fast your computers are. And yeah, my computer probably will take the 20 seconds. So okay, so it shows the status. Okay, it's finished. The solution times takes 16 seconds. So now it will automatically, the results will automatically load the data we just calculated and update the results in the graphics window. So for example, here the default is velocity. So it shows the velocity magnitude here. So this is the inlet gas that flows from here and flows out. So you will immediately realize that in the inlet it has a higher velocity, and outlet also has a higher velocity. But in the boot reactor, the velocity is pretty low because they are doing the reaction there. Okay, so this is we finished these calculations. Alright, so now we are going to analyze the results. In this file, we already have some the output. We already have some results like the velocity. So here it shows the inlet flow velocity, and the gas flows in from here and flows out. So and this the white area is the wafer area, and this blue one is called the boot reactor. And suppose we are going to analyze the silicon deposition rate. Alright, so now I will show you how to do this. And then here we right click on the results. We are going to show the 2D plot group, and here I give the label. Let's write the data silicon. Alright, so the data set, suppose I use the default. If it's not, then I can change it later. So the parameters value here, we do the calculation at V0 at 1, 1.2, and 2. So suppose we choose the 2. Okay, we choose 2 and we write on the dirt silicon again. We choose the surface. Surface means we are going to generate a 2D model. And here the surface label, which is V0, V0 equal to, I can put this label. And the data set from the parents, do not change it. In the expression, I type the dirt silicon. So, okay, dirt silicon dirt. And alright, so then we click the plot. Okay, so now we get this silicon deposition rate at V0 equal to. And you can see here, this is the boot reacting. So since the silicon deposition occur everywhere, so in it this process also occur in the boot reactor. But we mainly care about the wafer part in this rectangle area. So to do this, we need to use the dataset. As I talked in the slide, our previous slide, to do this, we need to set the dataset. So now I will show you how to set this dataset. Now I show you how to use the dataset to define the targeted data for the further analysis. So we come to the dataset and we do the right click and choose the solution. For example, if I want to get the data for the wafer, then I can give a label wafer here, and then I right click on the wafer and select the selection. In the selection, I need to select the wafer. So we click the entire geometry and choose the domain, click the menu and choose the wafer. So the wafer is highlighted in green here, which is domain 2. And now we finish this dataset. And then we come to the dirt silicon here, and we choose the dataset here. We choose the wafer and let's update the figure. So now we only show the data for the wafer area. In this part, I will show you how to read and analyze the exported data from the COMSOL using the MATLAB software. The MATLAB code can be downloaded from the course website here. Now let's start the MATLAB. I already downloaded the MATLAB code, analyze data from the course website into the folder MATLAB. Remember, you need to also put your COMSOL data into the same folder. So here I have 2 exported COMSOL data. One is called dirt silicon V0. The other one is called LPCVD data. So now let's show how to run the analyze data MATLAB code. So you can use the help command to get the instruction for the analyze code, analyze data. So we type the help analyze data. So we get instruction here. This function will read LPCVD data produced from COMSOL and do the conclusion, and will show you a plot. And the usage is to type the analyze and run the bracket and your file name. So now let's do it. So I can copy here. I can copy analyze data, LPCVD data text, since I already have this file. So now I click the enter. Let's see what results we have. So okay, the output is here. One is this figure, others output is here. The data, we have 100 data points, and for each point we have the percentage difference for the value. We also have the effectiveness factor for the silicon deposition rate. Here we have the 100 data points. This is because when I do the conclusion in the study option, I set the 100 data points in the Z direction. So if you set the 20 points in your conclusion, then you are supposed to get the 20 points here. If you set the 50, of course you will get the 50 points here. And also you can modify this analyze data code and make it more powerful. For example, you can change this code and to read more data, to do more analysis, or you can also design your figure and make it look better. Okay, up to now we have finished the whole lecture on the LPCVD simulations, and now it's your job to do the study and the practice. So thanks for watching this video and enjoy your COMSOL.